Okay, in this video I'm going to talk about stress concentrations and look at an example problem from stress concentrations. Now, in class we already saw that, first of all, here's one sample stress concentration chart. The sample gives the geometry, the loading, it gives the sigma zero, for which the final stress is based. The final stress is the stress concentration, Kt, times the sort of naive nominal stress. In this case, that would be the stress, the naive stress right through the hole would be our sigma zero. Okay, and so there are lots of stress concentration charts in the back of the textbook, and I will leave it to you to take a look at those. Let's take a look at an example. An example, what we have is this lug, which has a cross section with a thickness and a width. That lug is being loaded by a rope at the top. Now, I guarantee the table is not going to have stress concentrations for a lug being loaded by a rope, okay? And so what we're going to do is use a slightly different table that would simply have a rectangle with a hole under axial tension, okay? And we would be instructed to base our stress concentration on the area through the hole, or to base our final stress on the naive stress, which subtracts the area through the hole. And in this case, they're saying, let's take a look at not only stress concentration as the hole gets bigger or smaller, but let's look at the overall safety of the part as the hole gets larger and smaller, and recognize that they're not necessarily the same thing. That maximum safety for the part is not necessarily smaller stress concentration factor, because we know that as the hole gets bigger, the stress concentration factor gets smaller, but the stresses are going to get larger because the hole is bigger. It's removing more material. So we're actually going to calculate that effect. Okay, and so stress concentration factors based on values of D over W, going from a very small d to here the diameter is half the width of the part, a pretty large D, and we can see our stress concentrations heading downward. And this is coming from table A15-12. I'm not going to jump there and show that because I didn't prepare for that, but that says it is a square-ended lug. Matter of fact, let me see, can I show that? No, I don't have that table handy. So we're just going to trust their stress concentration factors, okay? And then our sigma max is going to be the stress concentration factor times our simple stress or naive stress. And our naive stress is going to be a force over area, but it's going to be an area that removes the diameter of the hole from the area calculation. And what they're saying to do is let's come up with a new stress concentration factor, which is based on sigma max based on the hole, but compared to force over area as if there were no hole. So they're saying it's insightful to base stress concentration on the unnotched area. So let's define a new K prime, which is based on F over W times thickness, ignoring the hole diameter. And that K prime might be a better indicator of how the hole messes up the stress situation. And so by setting this sigma max equal to that sigma max, we can come up with this K prime thing as a function of hole diameter, and we can plot it. And that's maybe the interesting part. Now, a power regression curve for the data is certainly unnecessary. I'm going to leave that to you to take a look at. They just did a little curve fitting to make it more interesting. I don't actually understand why. But now this KT prime says if we want to compare the actual stress to the force over dumb area, full area, we have an 8, a 6, a 5, a 4.81, 4.7, 4.69. It's been going down uniformly. But then as we go back, as we continue to go higher in hole size, the stress level starts to head back up because we're starting to consume too much of the material. So it looks like 0.5 area is the one that we see as being most effective. And if you actually were to take derivatives of the equation and set it equal to 0, the standard calculus way to find a max or a min, they say it's at a point of 0.483, somewhere between 0.45 and 0.5. Okay, so that would be a stress concentration problem. The key thing is understand that every stress situation has a stress concentration chart and a sigma zero equation that we use to calculate the nominal stress by which we multiply the stress concentration factor.